So we're going to be looking at a tree data structure and try to understand what it is, how it looks like, and every other thing around a tree data structure. But before we get any further, we need to understand what a tree is. And a tree is a nonlinear data structure that mimics a hierarchical tree structure where each node represents mark each node represents a point in that hierarchy. And what you have here, just to understand it visually, what you have here is an example of a tree data structure. And a tree is basically composed of two things. It is composed of nodes and edges. Now, what we have here, this sort of we've represented as circles. These are the ones that we refer to as nodes, and the lines connecting each of the nodes are what we refer to as, these lines are the ones that we refer to as edges, right? Now, the topmost node that exists here, we refer to it as the root node. So this one we call it the root node. And every other node is connected by an edge from its parent node except the root node, because as you can see, the root node is there. This is the first node here. So each of the other nodes that are going to come from here, they're going to be connected to a parent node. Now, to really get a hang of this, we need to understand a number of terminologies that we're going to be looking at to understand what trees are, and they're going to be really predominant in some of the things that we're going to be looking at. Now, like you've mentioned, the topmost basically node that we have here, we refer to it as the root node. And the root node is basically the starting point of the tree where the entire structure basically originates. So the entire structure originates from this root node. So you can just say entire structure originates from here, from the root node. Now, apart from the understanding what a root node is, we also need to understand what a child node is. And to understand a child node, basically a child, we're going to just have the terminology here on the side. We have a child, and a child node is basically a node that is connected to another node above it called a parent. So if this is the parent node, this node that we have here, if this is the parent node, then this is going to be the child node. Also, this parent node is a child node to the root node basically that we have here. So nodes below the root are called children. Now this is the root node. Every other node below it is called a child, but each child itself basically can be a parent. So as you can see, for example, this is a child node to the root node, but it's still a parent to because it has one more other nodes attached to it. Right? Now, apart from understanding what a child node is, we also have a parent node, and a parent node is basically where the child node originates from. So a node is called a parent if it has at least one child node. So if it has at least one child node, it is a parent node. So for example, this will refer to this as a parent node. Again, it is also a child node to the root node from what you've seen previously. The other terminology that we need to understand here is what we refer to as the edge, and we've already seen what the edge is, but the edge ideally is this line or the connection between two nodes. So the connection between a parent node and a child node. So it basically represents the relationships that exist between each of the nodes that exist in a tree data structure. Apart from the edge, we also have a leaf node. And just from the term itself, and in the context of a tree, of course, leaf nodes is basically the nodes that are at the end of a tree. So these nodes have no children. An example is in the structure that we have here. This is a child node. Of course, it's a child to this, which would be a parent, but it is also a leaf node. So this is a leaf node because it has no children. So all these are going to be leaf nodes, as you can see them here. Now that we've understood what leaf nodes are, The other terminology we need to understand that is really important is what we refer to as depth, or depth basically. And depth is basically, we refer to the depth of a node as the number of edges from the root node to the node. So for example, if you want to check the depth of this node here, we're going to basically count the number of edges from the root node. So the root node is here. To get to this node, we have 1, 2. So it has a depth of 2. Now, apart from depth, we also have another terminology which we refer to as height. And height is also really important to understand, since the height of a node is the number of edges on the longest path from that node to a leaf. So basically, the number of edges on the longest path from that node to a leaf. Yeah. So that's also what would refer to as height. Then we'll go ahead and look at a subtree. Subtree. We're going to be calculating this as well as we proceed. And a subtree is a portion of a tree that qualifies to be a tree itself. So an example here is we can just represent it like this. So for example, what you have here, this could be this qualifies to be this qualifies as a tree node, right? So we can represent this like that. This qualifies to be a subtree rather. So this is a subtree, and this other one could also be a subtree if we represent it like this. Right? So they're all subtrees because they qualify to be sort of trees on their own. And these are some of the key terminologies that do exist when we are referring to, or when we're learning about the tree data structure. And I hope that we have a good understanding of all of them up to where we've reached now. So now the next thing we're going to be looking at is the types of trees, and we're going to highlight the types of trees. And after that, we're going to be looking at into these trees in more detail in some of the next sessions. So we also have now types of trees. And when you talk of trees, they're different types, right? So they come in various types, and each type is suited for different use cases. So again, to just have a look at some of these trees and their use cases. Now, the first type of a tree we have is a binary tree. We have a binary tree, which is a bit well known. And a binary tree is a type of a tree where each node can have at most two children. So it is often referred to as the left child and the right child. So an example is the one that we have here. This could qualify as a binary tree because it has at most two children, the left child and the right child. And apart from a binary tree, we also have a different type of a tree known as a binary search tree. So we have binary search tree. And a binary search tree is also an interesting one, since basically it is a binary tree but with an additional constraint. And the additional constraint for a binary search tree is that for any given node, the left child must have a smaller value than the right child, and the right child must have a larger value. So if you were basically looking at numbers, this in terms of value, if zero is the one that is of the least value, so the left child would have zero, and the right child would have maybe 1, 2, or 5. Yeah, so that is what we refer to as a binary search tree. The other type of a tree we have is a balanced tree. So when you talk about a balanced tree is basically, in a balanced tree itself, the height of the left and the right subtrees of any node differ by at most one. So that is in terms of the height, they differ by at most one. And this ensures that operations like search, or rather makes operations such as search and insert a bit more efficient. And we're going to be looking at them, of course, in some future sessions. We also have a heap. And a heap is a specialized tree-based structure that satisfies the heap property. So basically, for a max heap, the parent node is always greater than or equal to its children. But we're going to be looking at the heaps later on in separate sessions. And the last one we have is a trie or a tree. Let's call it a trie. This is a type of a tree where basically it's used to store dynamic sets, and especially for string searching. So basically how it works is that each path down the tree represents a prefix of the stored keys, right? Again, I know that might not make so much sense, but when you get into looking at each of these individual trees, they're going to make a bit more sense into what they are. Now, the major question that I'm sure everyone is asking is, why are trees so important? And the reason why trees are so important is that they are widely used in a number of scenarios where they are efficient. So, like when you're dealing with hierarchical data representation, or when you're managing sorted data, or when you're doing basically fast lookups in a search engine, file systems, even the way the systems, or rather the folder and file structures in our laptops and our machines works. There's trees are used to that, and there are many more other places where this are used. But so far, this wraps up what our basic introduction into trees. We've learned about the basic structure of a tree data structure, some key terminologies that we've seen, which are going to be really key as we're proceeding in different types of trees. So in the next session, I'm going to be looking at deeper details into binary trees and how we try and make them a bit more efficient. Thank you, and I'll see you in the next one.